Okay, so our last topic for Unit 4 is about nonlinear systems of equations. We're on page 37 in your packet, and we're going to look at a lot of things that we've already done in sort of combinations to be able to talk about these nonlinear systems. So I want to start with something that we did just a couple lessons ago. Okay, so we're going to start with solving an absolute value equation by graphing. So this is something we have done recently. Okay, so I want to graph this absolute value function. This -1 here tells me that I'm going to move to the right one. The +1 here tells me I'm moving up 1. That's my corner. And then the negative in front tells me I'm going to be flipped upside down. So to get my sides, I'm going to go down 1 and out 1 on either side. And then I'm going to continue that to the edges of my coordinate plane. Once I've got my points plotted, I want to connect them so I can see the graph of my absolute value function. And then I want to graph the other side of my equation, -3. Remember that that's a y value. I'm going to go to where y is -3, 1, 2, 3. And I'm going to stretch that all the way across my graph. And I'm looking for where those two things intersect. Those are my solutions. So I have a point of intersection right here and right here. That means my solutions are x equals -3. That's the x value for this point. And over here, this would be x equals 5. Familiar? Yeah, we just did this, right? Okay. So solving absolute value functions by graphing. Okay, something we can do, something we've done recently. Now, let's make one tweak to this. If I look at the function right below, the equation right below, we're going to solve this one by graphing as well. So we've got an absolute value thing, but then on the other side, instead of just a number, which gives us a horizontal line, we've got a little linear equation there, a little y equals mx plus c deal. Okay, so we're going to treat this exactly the same way. We're going to start by graphing what's on the left, which is that absolute value equation. I'm going to move left 1 and down 4. So left 1, down 1, 2, 3, 4. There's my corner. And then that 2 in front tells me the slope of my sides is going to be 2. So up 2 and out 1 on either side. I'm going to continue that across my coordinate plane. And then connect my points. So there's the absolute value portion. And now this time my line isn't going to be horizontal. It's going to have a slope to it. So my y-intercept here is up at +2. And my slope is 2/3. So up 2, 1, 2, 3. And then some points back this way, down 2, back 1, 2, 3. Down 2, back 1, 2, 3. Right, we've graphed a million lines by now. And I'm going to go ahead and connect those. So I have the graph of my line. Where do you think my solutions are? The intersection points, exactly the same idea, right? The only difference is instead of having a horizontal line, now our line has a slope to it. But my solutions are still at those points of intersection. So my solutions would be x equals, this is -3, and then x equals, this guy's at +3. Okay. My equation looks a little different, but we solved it exactly the same way. Okay. Questions for me so far? Okay. So turn to the next page and we're going to take this one step farther. On the next page, our functions are already graphed for us. I'm going to do a little color coordinating here just to make this a little easier to see what we're talking about. So f of x is a function that we haven't talked about in here. This is a rational function, and we'll see those in algebra 2. But for right now, the important thing is that we can pick out what the f of x graph is. So that's this piece and this piece. Rational functions sometimes are split up into pieces. Not important that you know anything other than those two chunks are that f of x function. And then g of x is an absolute value function. So that's our v-shaped function here, our v-shaped graph. Now, with everything that we've done in this unit, sort of rattling around in our brains, we've solved linear systems of equations before. When I graphed a linear system of equations, when I graphed two lines, where was my solution? What did I look for on the graph? Where they intersected, right? So here I've got a system of equations. They're not lines. What do you think I want to look for on the graph to point to as the solution? Where they intersect, right? It's exactly the same thing. The graphs are goofy, but the idea is exactly the same. So the solution to this system is that point of intersection, okay? The solution to this system is 3.742, 1.258. When we had lines, we looked at where did they intersect, that was our solution. Here, I've got two graphs, they aren't lines, but the solution is the same, okay? I look for where they intersect. What are these other points? The other labeled points, what are they? They're, yeah, just our x-intercepts for the graphs. I've got two x-intercepts for my absolute value graph. I've got one x-intercept for my rational function, but they're just x-intercepts. Questions for me so far? So this problem is new for us today, but the ideas that we use to come up with our answers, those are not new ideas, okay? We've used those for a while. Let's take a look at example 3 down at the bottom of this page. I'm going to color coordinate again. They didn't give us the equation or the function for f of x. It's labeled on the graph for us. They didn't give us the equation for g of x either. It's just labeled on the graph for us. I'm going to go ahead and just draw over them just to make it a little easier to see, make it a little easier to talk about. Okay. So what we're going to look at here is kind of a throwback again to something we've already seen before. We've got function notation as we're talking about this problem, just like what we saw in Unit 2. You also saw some function notation pretty recently. I threw a couple of problems at the bottom of your last quick check about function notation. So remember when I'm asking questions like f of x equals 4, what I want you to tell me is what x value makes that true. So this is a y. I want to know what's the x value that gives me a y of 4. So f of x is our yellow graph. So I'm looking on the yellow graph for when I have a y value of 4. So y is 4 up here. If I were to treat this like our absolute value equations that we were solving, I've got 2 points on my absolute value graph that have a y value of 4. So x could equal 1, or x could equal 5. If I gave you the function for f of x, we could write the equation for this absolute value graph. I know it has to have a negative lead coefficient because it opens upside down. From the corner to the next nice point, I go down 2, so it'd be -2 times the absolute value of x. We moved 1, 2, 3 to the right, so -3. And then we moved 8 up plus 8. What I'm asking you to do here is solve when does my absolute value equal 4? So I gave you this question a couple days ago. You would have graphed your absolute value function and then graphed 4 and said x equals 1 and x equals 5. Exactly the same thing here, except I didn't give you this to graph. I just gave you the graph of the function. Okay? So now same idea, but with g of x. So I want to know, when does g of x equal 0? So remember, I'm going to where y is 0, and I'm going to stretch that across my graph, and I'm looking for when I hit the green. So we hit the green right here. So g of x equals 0 when x equals 5. For our next problem here, I want to know, when is f of x equal to g of x? So what am I going to look for on the graph? Where they intersect, yep, where the green and the yellow hit. So I've got a point down here where the green and the yellow touch, and I've got a point up here where the green and the yellow touch. So let's approximate those x values. This one's not at a nice spot, so I'm going to say it's maybe about -3.5. And then this one looks like it's about 6. Hard for me to tell with my coloring over stuff if it's exactly at that corner or not, but it looks like it's about 6. This is the same idea as what we've just worked on, solving our absolute value graphs. Just this time, I'm not necessarily looking for when does this line cross this absolute value graph. I'm looking for when does this one graph intersect with this other graph. They don't have to be an absolute value in a line. They don't have to be 2 lines. They could be any 2 functions. Questions for me so far? Okay. And then our last question here on page 38 asks about g of x. So that's our green graph. And it asks, when is g of x equal to -6? So -6 is down here, -6. If I stretch that across my graph, that's right here. Where do they touch? They don't, right? So what would I put here if they don't touch? No solutions. G of x is an exponential function, and we'll talk about those later on in Algebra 1. They have something called asymptotes, which is a fancy name for a line that they never touch or cross. So that's actually what we're seeing with this last problem. The important thing for us right now is that the green graph doesn't ever touch that red line, so that means no solutions. And we saw with some of our absolute value functions that we solved by graphing, where we had our absolute value v that never touched that line and it was no solutions. Same idea here. Questions for me so far? Okay, yeah, just a couple more examples we're going to look at together for today. So if you would for me, please turn the page again. For example 4, speak this down. For example 4, they gave us the functions for f of x and g of x again this time, but we're also given the graphs. Now these aren't things that we have learned how to graph yet. This is an exponential function, and we'll talk about those again later in Algebra 1. This is what we call a log function, and we'll talk about those in Algebra 2. But the important thing is that I know what the graph looks like. So here's f of x. Again, I'm going to color coordinate. And here's g of x. And for example 4, this time we are going to write the equations. So I want to write 3 equations. I want all of them to have x equals 1 as a solution. So that means when I look at my graph, x equals 1 should be that value that I care about. Anybody have an idea for something that would have a solution of x equals 1? Anything interesting happen when x equals 1? There's a 2 for the y value. Okay, there's a 2 for the y value. So what that means is that for f of x, our yellow graph, when y is 2, x equals 1. So what I can say is if f of x is equal to 2, if f of x is equal to 2, if 2 is the y value, then I have a solution of x equals 1. That also works for that green graph too, doesn't it? So for g of x, this is also true. When g of x is equal to 2. So if I gave you this equals 2, you would graph this, and then you would look at when is it equal to 2? What's the x value there? Well, the x value is 1. That solution is 1 again. Yeah, and then the other interesting thing that happens here is that both of those values, since they both have an x value of 1, when their y value is 2, that means that when f of x is equal to g of x, if I looked at what's the solution to this system, where do they intersect? That happens when x equals 1. Very good. I have that intersection point when x is 1. That's where they cross. So if I were to set those functions equal, the solution to that would be x equals 1. Questions for me on example 4? Okay. Now, when we talk about linear systems of equations, I have 3 options for solutions. Okay. So for linear stuff, just jot some notes down over here. I could have one solution, and that's when I've got lines that cross each other. I could have 0 solutions, and that happens when I've got parallel lines. Or I could have infinitely many solutions, and that happens when I've got the same line twice. For nonlinear systems, I have a ton of different options. We've already seen some examples with 2 solutions. I would like you please to take the next couple of minutes and give me a sketch of something that would have 2 solutions. Give me a sketch of something that would have 3 solutions, and give me a sketch of something that would have no solutions, okay? I want you to not give me 2 lines, okay? One of them could be a line and one of them has to be something else, or neither of them could be straight lines, but I don't want you to just give me a system of linear equations, okay? One of them can be a line, that's fine, but not both of them. So sketch for me an example of a system that would have that number of solutions. We've already seen some nonlinears with 2 solutions. Questions?
Is that curve looking thing a line?
Lines are straight. If it has any curve at all, it is not a line. So that would be fair game.
I attempted.
For our two solutions graphs, I saw a lot of absolute value graphs intersected with lines, and that works. I also saw some absolute values intersected with other absolute values. That works. We've got two solutions there, just like we have two solutions here. I also saw a couple people do an absolute value intersected with a parabola, intersected with one of those x squared functions that we had talked about earlier this year. And that works too. That's two solutions. If you had something different than either of these, but you still had 2 points of intersection, that's also great. No solution, I saw a lot of absolute value graphs with a line that did not touch it, a line that was below, or if this was flipped, a line that was above. And so we saw those not that long ago when we were talking about solving absolute value functions with graphs. So that works. I saw some other sort of variations on that, either with maybe another absolute value that opens the other way, or an absolute value going one direction and a parabola going the other. As long as they're not intersecting, that's no solution. Where we seem to have a hard time is with the three solutions. That's okay. You guys haven't seen all the different types of functions and what their graphs look like at this point. So I saw some sort of creative problem solving as I walked around. But one option might be something like this that I cut with a line. This isn't the only option, but that would be one of them. As long as I have 1, 2, 3 points of intersection, we'd be okay there. One of my graphs is probably going to need to be a little curvy to get 3 solutions. Questions for me for today? Okay. I will tell you that when you see questions about systems, nonlinear systems on your tests, they're going to be most similar to example 3, okay, where we bring in that function notation and I'm giving you that graph. If it's not a linear system and it's not an absolute value function that I'm asking you to solve, I will more often than not provide those graphs for you. So test questions over the stuff you can expect to look like example 3, okay? For the rest of class today, I have a delta math for you over nonlinear systems. So you will have the graphs and you are looking for those solutions. You are looking for those intersections.